John says, I'm Peter Chipchase. I'm a director at WSP, and I'll be talking this afternoon about how we can reduce our carbon footprint by refurbishing, repurposing, modifying, and ultimately reusing existing stadium structures rather than knocking them down and starting again. So, through my career as a structural engineer, which is now in its 27th year, sustainability has always been an important consideration in building design. But it seems as though it's only been in the last few years that it's really moved to the top of the agenda. And we hear the terms climate crisis, climate emergency more and more. What's becoming clear is that it's of vital importance that we, as building designers, do everything that we possibly can to reduce carbon emissions associated with the buildings we design, so that we can limit future global warming to within manageable levels. So what does that actually mean, and what does that actually look like? Well, I think it means that it's up to all of us to do our bit. So at WSP, we've set out effectively a sort of a timeline towards what we have made a commitment to achieving, which started with back in 2017, when we sort of effectively set our targets as to what we were going to achieve towards that goal. In 2020, we made a pledge, a commitment to halve the carbon associated with our designs by 2030. We have committed to become net zero carbon in our operations by 2025. Achieve those 50% reductions in emissions associated with our designs by 2030, and then ultimately by 2050 be net zero carbon in everything that we do. So how do we go about doing that? Well, as a sort of global multidisciplinary engineering company, there's quite a lot we can do, and quite a bit of it is not necessarily associated with the buildings. It's about infrastructure and energy, but I won't go into that today. When it comes to a building's point of view, we obviously can do lots of things to reduce the operational carbon, and there's other also things that we can do to reduce the embodied carbon. And I think it's fair to say that certainly over the last 20 years or so, we've made great strides in reducing our operational carbon with things like Part L coming in, and also things like greening of the grid and improvements in efficiency of MEP and facade performance and things like that. But I don't think we've done anywhere near enough in terms of the embodied carbon, and that's the sort of focus on what I want to talk about today. Excuse me. So there's a number of tools that we have developed to help us try to reduce our embodied carbon, and also to monitor embodied carbon in real time as we design buildings. So there's obviously the use of timber, which is being promoted, as discussed earlier. Material specifications are all being updated, and we can monitor the carbon in real time by having we have a tool here similar to the Struct-E tool, which is linked to our Revit model. So it enables us to monitor carbon and also identify where there are hotspots in our designs. But that's all really sort of down at the right-hand side of this famous diagram, courtesy of the Struct-E. With the best intentions, there aren't big returns in that kind of thing. So what we really should be focusing on is trying to move up towards the left-hand side of this, and that's things like, as Knut mentioned earlier, designing facilities so that they're multi-purpose, modifying them where we need to rather than knocking them down, and ultimately, the goal is of building nothing. But the problem, of course, is that facilities are designed for a particular age, a particular purpose, a particular set of uses, and typically, as you go through the building design lifespan. Life moves on, things change, requirements change, and therefore it's difficult sometimes once you get into 50, 60 years of a building's life. It's not necessarily fit for purpose anymore. So what I'd like to do is just go through a couple of examples of projects where we have tried to do what we can in order to minimize the amount of additional new structure, try to retain and just augment and add to, modify where necessary. Now, I should say at this point as well that this obviously takes you can't do this by yourself. It's a team effort, and particularly it relies on clients to have the vision to want to keep the facility, given what I said about the fact that a lot of the time it's just easier to knock it down and start again with something brand new. But in the case of the Montreal Olympic Stadium, the client very much wanted to retain what is a very recognizable building and bring it up to modern standards so that it could be used in the future. It's a highly unusual structure, as you can see from this image, and there's not too many stadia around the world. Well, certainly not with the tower supporting part of the roof, but not many even with a primary structure of the roof being in concrete. A precedent to this is Parc des Princes, which is same architect, Roger Talibert, but it's highly unusual in its construction. I'll explain the construction in a bit, but some of these site photos taken during construction just to illustrate the scale of this. So the concrete cantilevers here that you can see are up to 55 meters. This technical ring which links them together at the oculus is sort of 5.5 meters deep, but when it's up in the air it looks quite small. The scale is huge, and interestingly, considering this was built in the early 70s, most of the stadium structure itself is precast concrete. So it was built initially, the first phase was for the 1976 Summer Olympics in Montreal, but it wasn't completed for that. So this is a view of what it looks like, or sorry, what it looked like in 1976. That's the opening ceremony, and you can see the sort of the stub of the tower there in the distance. So it existed like this for a number of years after the games, and it wasn't until 1987, I think, where the tower was completed, and the first roof was installed to make it a convertible space. So this is a roof of Kevlar, which is retractable, as you can sort of see, up into the niche up here. And unfortunately, that roof was only retracted and deployed 30 odd times, and it failed under wind loading. So it was replaced. Oh, I should actually, because this is quite important, just understand how the roof is supported by the existing structure. So it's generally hung from the tower, but there's also a peripheral support around the oculus, partial support, and then there's also a big horizontal force as it sort of to restrain it against the base of the tower. So the Kevlar roof was taken away and it was replaced with the roof that is still there today. So that is it's not retractable. It's a fixed in place roof, which is different, completely different in its construction. It's got an upper membrane, shear fill, and then basically two cable nets, an upper and lower cable net, propped apart by some struts, and all stressed against this compression ring around the perimeter, which actually, even though the roof is supported by the tower, it actually puts upward forces around the oculus. This roof, unfortunately, wasn't designed for current snow loading in Montreal, and it suffered a partial failure. And so now what has to happen is that in order to mitigate the snow accumulation, hot air is pumped into this enormous void. So that's the soffit membrane, that's the upper membrane. Hot air is pumped into that void to melt the snow, but still it's not safe to use the stadium when there's a significant chance of snow in Canada, which is obviously a significant part of the year. Also, the upper membrane isn't robust against ice fall, so there's quite a bit of ice falls down from the tower and the cables, and all of these little patches here are where the membranes had to be repaired. So not ideal. So the client, the brief effectively is that the client wants to replace the existing central roof with a roof that can support future wind and snow and everything else without mitigation, can support modern event loadings to allow it to be able to be used for multiple events, is robust against the ice fall, can be ideally supported by the existing structure without strengthening, provides a thermal barrier, complements the architectural form, but predominantly, fundamentally allows the stadium to be used 365 days a year for toast any event within reason. So as I said, we're working with, and Philip mentioned earlier, we're working with Schleich Bergman on this project, and the first thing that we had to do was work out what the capacity of the existing stadium is, both in terms of the tower and the stadium itself. So that involved research of more than 50,000 record drawings of everything, which enabled us to build up a geometrical model like this one, which was dimensionally representative of the existing stadium. And it's, as you can see, it's very detailed, and it's very unusual and very complicated. We then point cloud surveyed the entire thing and made adjustments to that geometrical model so that it was representative of what is actually there. And then the next thing was that we went through an exhaustive, extensive regime of sampling, monitoring, testing of materials in order to be able to populate the various models to turn them into analytical models. And I should just explain at this point the construction of this is obviously the tower. So it's concrete up to about this level, and steel above, for reasons I won't go into now. Post-tension front wall, post-tension back wall, and then the steel part above here. The walls are double plates with stiffening ribs, sort of ship construction. And the whole thing is supported over this sort of grillage of walls, so that it spans over so it's only supported at 3 points. It's only supported these 2 points and back. So there's a big swimming complex underneath. So just to make things even more complicated. So once we'd been able to populate the analytical model, we used, in this case, it was Abacus, in order to investigate how what the true capacity of the tower was in all of the bits by progressively increasing the load. So we had the load applied here, which is the load from the cables that support the roof, and we incrementally increased the load, capturing all of the geometrical and material nonlinearity to give a true picture of how that tower actually performed. And that allowed us to calculate then what our sort of serviceability and ultimate limit states were, so that we could convert those to an allowable force. And we did the same exercise on all of the rest of the components of the tower, so that and recorded what the capacity of each of them were to give us effectively where our sort of weak points were. So the it just so happens the tower was a weak point, and these were our SOS and ULS forces that could be taken by the tower. Same exercise or similar exercise for the stadium. So the stadium primary structure is this array. The red things are what we refer to as consoles. So they are precast. Typically everything is precast. So they're precast segmental concrete units, which are then post-tensioned together like this, and they're sort of balanced. So the idea is that that there's not much of an overturning moment on the base, although there obviously is. But as I mentioned earlier, the scale is incredible. That from that's 55 meters. That's 5.5 meters. Everything is huge, and again, we were able to from the record survey information and materials information, we were able to build up again using Abacus detailed FEAs that looked at the interaction between the tendons and the concrete to again incrementally increase the forces at the oculus to give us an idea of what was happening within the structure, again capturing all the non-linearity, mostly material in this case, to give us the load. In this case it's moment rotation, but it gives us an idea of what the capacity ultimately is at the oculus. So we could then give those forces to our friends at SPP to say, okay, the new roof that you're going to design in here cannot exceed these forces. Otherwise, we have to go into strengthening, which we want to avoid. And so SPP obviously then looked at lots of different options. And the important thing to start with about that was that the upper profile then affects how the wind and snow load are going to accumulate. So we all agreed on a sort of fairly aerodynamic dome form, like it's not a structural dome, but a geometrical dome, and that was then wind and snow load tested, because again in Montreal snow is significant. The client doesn't want any snow mitigation. They don't want to have to get rid of snow, and so this was effectively snow tunnel tested by RWDI to calculate, as well as being wind tunnel tested to calculate, taking into consideration the effects of the tower and everything else, and look at the snow loads and the wind loads, because of course they then had to be subtracted from the reactions, the allowable reactions, to give SPP the loads to be able to design the new structure. And just to give you an idea, that quite a bit of this is subject to sort of over 3 kPa as snow load, and then where the snow drifts up against this step change, we're up at something like 5.5 kPa of snow, which is it's almost 2 meters of snow. So it's a lot of snow. So anyway, so that after that had all been taken away, that could then be converted back to the sort of residual forces that could be applied to the existing structure. SPP then worked their magic and came up with a very nice sort of truss grillage that's partially supported, as previously, by the tower, and then the perimeter band then spans back onto the edge of the consoles, and all works fine. But I think the sort of crux of this, and the most important thing about all of this, is the carbon story. So if you look at the existing stadium structure, being the sort of nature that it is, and these values are approximate, but they give you a good order of magnitude. We're talking about something like 136,000 tons of embodied carbon, which is 730 kgs a square meter, which from the chart is off the scale in the wrong way. But if you then but you're not building that, you're keeping that, and you're only building the new bit. So you're only adding 6,700 tons. So if you apply that across the existing area, you're 36. It's 5% of what it would be if you were to build this thing again. So you're quickly in the A** rating by retaining your existing structure rather than knocking it down. Another example in a sort of similar vein is this. This is a project. It's an existing stadium in the UK, which I can't say which one, but the client wanted, in the theme of multi-purpose, multi-use, wanted to be able to use the stadium to host other events. So they wanted to be able to have a roof, a retractable roof that enabled events that are sort of semi-internal, not hermetically sealed, but weatherproof, so that they could host events, keep everybody dry, but also didn't want to, wanted to avoid, as far as possible, strengthening the existing structure. So in order to do that, we weren't actually able to do that, but what we were able to do was concentrate the forces, design this to concentrate the points at which strengthening was required to only 4 points, and everywhere else doesn't need to be. And in order to achieve that, and this partially to keep the weight down, but partially because the client was very keen, the primary structural elements are, the majority of them is in a carbon fibre reinforced polymer. So all of the black that you can see there is carbon fibre, and the white is steel, and then the blue is the retractable membrane, which I'll describe a bit more in a bit. And so, but the thing about this is designed purely with the understanding of the carbon fibre material at the forefront. So a lot of people think of carbon fibre as being a sort of a wonder material that does everything. Of course, it doesn't. It's got good points. It's got bad points. It's obviously very strong. I mean, for a start, it's controllable. It's like reinforced concrete. It can be whatever you want it to be, but it's typically strong, or can be strong, but it's not very stiff. It is light, but it doesn't weigh nothing, and also it's very expensive if you don't understand how you can fabricate it to be less expensive. So one of the things that's expensive is fabricating unusual things out of carbon fibre. So node points, for example, are, because you have to make a mold up to make them. It's vitally important that you standardise those as much as possible. So the way that the geometry of the primary elements is set out is so that there's only 10 different types of these. There's 3,700 nodes, but there are only 10 different types. And I should mention as well at this point that this isn't an arch. This is a beam. It's a 3D truss that spans. It doesn't, and it's got roll. It's pinned at one end and roll at the other end. So it doesn't arch. It spans. And so the nodes are then modelled and designed. So as I say, there's only 10 different types, so you can reuse your molds multiple times. But also the connections between I'm sorry, I should say that all of these elements are all the same external diameter as well, and they're protruded to keep the cost down. So, and then all of the connections are these very simple sort of halving joints, which are glued. So you just bring along your next element, offer it up, clamp it, glue it, and then that's it, which is important for the sequence of construction that I'll come on to in a minute. So we modelled all of those connections, and also then how they interfaced with the membrane guide system. So this shows a detail of this is one of the shuttles that supports the membrane with the cables that drive that, and then the return cables up here. So this was all considered through. This is only a stage, we just finished stage 2, so there's a bit of development to be done on these, but the principles are sort of there. And also what we were able to do now is CFD analyze any shape to calculate wind pressures up front, rather than have to do a wind tunnel test immediately. And what that was, we still would probably do a wind tunnel test downstream to confirm these values. What it does in the early stages, that this is effectively, it enables us to get an idea of what the true wind forces are, because because of the nature of the structure, that you don't want to get in a situation where you miss something and then later on you have to fundamentally alter the principles of the design. So we could do that, and that they then translate into, as you can see, a sort of funny arrangement of lateral forces to be applied to the model, which all then fed into the analysis model. Analyze the usual thing under deflection, action forces, line stresses. You can see here, because of the carbon fibre there, some of the stresses are high, but nothing like the capacity. And also the shape of these things was designed understanding the fact that carbon fibre isn't very stiff. We obviously were concerned that these things might want to buckle, but they're designed so that the buckling is resisted by the elements in this direction. So the load factors are pretty good on that. And then coming back to the sequence of construction, again, the geometry and the proportioning of these elements was decided early on so that you can minimize the amount of construction traffic that you need to the site. So these are set out so you can get 12 of the sort of component parts on a truck. And then in terms of the temporary works and construction plant on site, that's again been designed with that in mind. So the sequence is like this: you install your ladder. You probably have to you have to hold that in place. Let's say 220 kilos, and then the other side. And then these bits are sort of 25 kilos each or less, so they can almost be installed by hand. And then you just repeat the process like this, and that builds up a quarter of one of these units, and they can then be lifted onto these reusable temporary towers connected together. And then once the thing is complete, because it spans and it works in the permanent case, these can just be, that's probably weighs 50 tons or something like that, 60 tons, so they can be tandem lifted quite happily onto the existing stadium. No works on the field of play, no impact on the field of play. They can just be put in place until the whole thing's finished. And there's just to sort of explain, everyone else is showing movies, so I'll show you as well. This just shows the relationship between the existing and the proposed. So that's roof surface. There are in the existing stadium these cable stays, so that's another reason for this being designed, to avoid those. But this is really to illustrate the principles of the retraction system. So you have the motors here, and they drive these deployment cables, which are connected to shuttles in a guide rail, which are connected to the membrane. And as they're pulled back, they just sort of bump into each other and gather up together as the membrane is sort of concertinaed, and that carries on until the end. And then it's basically the reverse going out to deploy them. They just get pulled out one after the other, and that continues to the point where they are then stressed to hold them stable, and then that shows it in the deployed state. So just then, coming back to the whole sort of purpose of this, the carbon story here is slightly, it's not as good news story as Montreal, because of the scale of the new roof compared to the scale of the existing. But in general terms, the existing stadium would be, say, 328 kilos a square metre, which is not too bad. That's a sort of E rating. If you were to build the whole thing, the existing stadium and the new roof, you'd be worse. You'd be 387 and you'd be an F. So it wouldn't be. And part of the reason for that is that the carbon fibre, even though the carbon fibre roof itself only weighs sort of about 30 kilos a square metre for a 145 metre span, it's pretty intensive in terms of carbon. So the roof alone is sort of 10,000 tons of carbon, even though it doesn't weigh very much at all. But even so, with it, because that's all you're building, you're not building the existing stadium. You're effectively, down at 150 kilos a square meter, something like that, was almost in a rating. So I hope I've sort of demonstrated the value of retaining existing structures and the potential for saving in embodied carbon, even if it's not to the same extreme as some of these. There's clearly some big wins to be had. Okay, thanks for listening. That's me done.